All right, so welcome everybody to today's presentation segment of SpaceBeer. This time today is going to be a bit more split up, actually. There is going to be a presentation from me and from my colleague for telecommunications, and afterwards we are going to have follow-up on onboard data handling from onboard data handling and software engineering team. By the way, I just want to mention that there is also a some sort of a contest going on, or well, there is a gift available today, or prize for anybody that leaves. I think just the highest amount of tip. I think my colleague is going to tell you more about that.
If you know the display over the bar there is actually a leaderboard. And who has the most points over this night, the evening, sorry, the person wins this nice T-shirt from our partner VZLU. I don't know the English abbreviation, sorry. And yeah, it can be yours if you drink.
If you spend enough.
Or spend enough, yes.
Oh yeah? Question?
Well, we can limit the contest till 8 o'clock, so we can actually select the winner right after our presentation.
All right.
Okay.
So time limit is till 8. We'll see how these presentations are going to go, because I think it's going to be a tiny bit longer than expected. Well, so let's at least start so we can get over it. So my name is David. I'm here from YSpace, from the communications team. I'm currently working in GroundCom, a startup company here in Brno, specializing in ground stations. Currently, I'm working there as an RF intern, basically. So my introduction to space communications is going to be quite simple, I hope. So everybody here can get to a specific level of sorts. So we'll see how it goes. I would actually like to hear feedback from you afterwards, whether this was too simple or maybe still quite complex. So we'll see. So outline for this presentation. First, I'm going to just briefly mention some electromagnetism basics. Afterwards, we are going to have introduction to signals. Then I'm going to go briefly through radio frequency bands, what they are and how are they assigned, maybe. And then hopefully I get to the part where I discuss digital communication diagram and its components, because that's the main goal for today. And then I also want to mention a couple of things about transmission channel. So about electromagnetism. So if we have a charge, let's say positive charge in space, around this charge there is going to be electric fields generated, of course. And in any point, anywhere around this sort of charge, we can somehow investigate what kind of power, or sorry, what kind of force is going to interact with an object we are going to place in that point. In this case, let's place another charge there. In this case, this is going to be 1 coulomb, just because this is how the definition goes. So this charge then is going to be pushed away or repelled by a force which is equal to the electric intensity of the field around this positive charge here. So how to interpret this really? I would say that let's have a steel rod or any type of metal rod. Let's connect some sort of actuating voltage or current source. It doesn't really matter. Now, what is going to happen to particles or, well, any, let's say, electrons? We know all that there are electrons inside of these rods. What is going to happen to that electron? Well, it's going to somehow oscillate or start to move around, well, based on actuating voltage source. So in this case, in any point here, there is going to be electric intensity of that field, right? That field generated around that electron. So as this field is changing, as these electrons are moving around, the intensity is also going to fluctuate. And this is basically the intensity in for example, this specific point here. It doesn't really matter. So as it oscillates, it also generates magnetic field. This was defined by Mr. James Clerk Maxwell in the second half of 19th century, I think, and he derived it with these phenomenal equations we call Maxwell equations. I don't like them personally because I'm too dumb to understand them. But I realized that I actually do not have to understand them. I just need to understand the general concept, and that's the most important part. So I promise no more math for today. So this is how it actually looks. So this is the electric intensity as it moves around, or well, as it fluctuates. And then there is also magnetic intensity or magnetic field present in this case, which is orthogonal to the electric intensity. So this is basically our electromagnetic wave we are going to use to propagate our signal through space. So our magnetic waves. To somehow prove this, we can imagine that there is another metal rod at a specific distance away from this first rod. In this case, what would the electron do after, of course, we would connect this sort of source and then turn the power on? Well, they would start to oscillate, and without any sort of connection in between these. So there is some sort of energy being transmitted through space. This is a very simple proof of this concept of electromagnetic radiation. Okay, so introduction to signals. I'm going to talk about signals. I promised not too much math today, so we'll see where this really gets us. But, well, most of you already know this equation of sorts. So we have some sort of an amplitude of a signal, we have some frequency of a signal, and then we also have phase of a signal. Now, let's just quickly interpret a couple of these values here so we know what we are on. So imagine amplitude of 1, frequency of 2 Hertz, this is how fast the signal is changing, and phase 0. So it would look like something like this. So now let's switch the amplitude so we know what's going on. Now let's try frequency, for example. Oh yeah, frequency increases. And then lastly, I would try phase. So let's go. It shifts along the time axis in this case. Wonderful. Okay, now to actually understand a couple of concepts from this lecture, we also need to somehow understand a different points of view, how to view these signals. We can view these signals in a time domain, of course. This is how we generally view our worlds, in time. However, sometimes it might be beneficial to actually move into a different space. And we do that by using transforms. In this case, we can use Fourier transforms, and we can transfer this signal to a different domain. And it's quite a difficult concept to wrap our heads around quite quickly. So let's just say that this happens. I somehow transform this signal to a different domain where on this axis, instead of time, I'm going to have frequency. In this case, this signal has frequency of 10 Hertz. And somehow, through the transformation, I obtain values at 10 here. So at 10 Hertz. But now, why is there minus? Why are there negative frequencies? Those don't exist. And why is the signal split into two? Well, let's just forget about that. We don't really need that. All we need is actually to view this as a tool that detects our frequencies obtained in the signal. Of course, everything else is also beneficial, but for our purposes, this is going to be enough. So, after transformation, I detect that there is some signal at the frequency of 10 Hertz. Good enough. Wonderful. Now, let's make it a bit more complex. So, let's say that we have all these components. So, these are different frequencies, also, I think, different amplitudes. So, let's summarize them. This is what we are going to get. This is a sawtooth signal. We can shape these signals as we desire. That would look like this after transformation. So we have multiple components here. Amplitude, yes, it's actually here, but let's just use it as, again, as a detection. So we have all these different components here. So this is how we are going to also view signals to understand it a bit more in depth, this entire system. Okay, so electromagnetic spectrum in general. So electromagnetic spectrum is basically a spectrum that we actually use, or well, we actually use every single day. It also contains visible light. Therefore, it's part of the spectrum, and even though we don't know it, it's basically all just a general. Let me start again, so it's a bit simpler. We utilize this spectrum in many different forms. Radio waves, which I am going to talk about today, are in the lower part of the spectrum, so signals with very, very low frequencies. The higher we go, the higher the energy is supposed to be, and also, of course, the frequency itself. Visible light is at very, very high frequencies, almost unachievable by today's hardware. But yes, somehow they are. Why is it now in millimeters here? Why isn't it in hertz? Well, there is this small relation to the frequency here that tells us that wavelength is somehow related to frequency, right? So basically, the bigger the wavelength, the smaller the frequency is going to be. Wonderful. Let's now look at radio waves. Okay, so first of all, let's list these from a perspective of a radio engineer. We split this spectrum into different bands, basically to better orient ourselves and to better pinpoint a specific frequencies we require for a specific use. So in this case, we see like navigation, and then we slowly go to radio, then to television, to mobile phones and GNSS, and then satellites. So higher we go, the more complex these systems may seem. It's not really that true. However, so this is like a general categorization of radio spectrum. In space, we usually use a different categorization, just so we can sort of distinguish even we can distinguish the spectrum, this part primarily of the spectrum, even better, so we know in which part of the spectrum we are operating with. It has so many different uses, so let's look into those after this slide. So now frequency allocation is a problematic thing. Frequency spectrum, as you could see, is actually how to say that properly? So it's a national heritage of sorts. It's similar to gold or maybe oil in some way. It's quite restricted. Why is it? Well, if I, as a radio amateur, would start to beam or start to transmit some sort of signal, and it wouldn't be controlled in a specific part of the spectrum, what I can actually do is I can interfere with other users that want to use radio frequencies anywhere else. So I need to actually control and actually look at what part of the spectrum I'm really using and stick to that part. And that is regulated and is actually punishable by law. So watch out for that for any radio amateurs. This right here is some sort of a allocation diagram. It goes from very low frequencies to high frequencies. And you can see there is a lot of allocations. We can utilize the spectrum on quite a large scale. However, it's going to be much more beneficial for us to look into amateur bands for us as students than any other like specific bands here where mobile operators can purchase parts of the spectrum, or even military can reserve part of the spectrum for their uses. So that is going to be restricted. Okay, so frequency bands for space. These are the bands, and I'm gonna just quickly list all the uses here. So the lower the frequency, the more limited the use can really be. So we are restricted by the amount of users, and usually at lower frequencies there is much more crowding. So this is usually restricted for some small communications, and the higher we go, the more data can we usually transmit, not because that signals are fast, but the spectrum is sometimes and usually more available for us. That's it. Okay, for communication in general, we list 3 concepts for satellites. We list downlink, uplink, and interlink. Interlink is quite specific, but that's what was listed in the previous slide, so I would like to clear this out. So this is just a routing of signal either from the ground station to the satellite or from the satellite down to the ground station, or communication in between satellites, which is a bit more advanced. Okay, so yes, I got here, great. I was trying to be fast, but I don't think I managed. Anyways, so this is a digital communication diagram. This is the system we are actually designing or trying to design as radio engineers. However, it can get quite complex, and as it is quite general, I would say that we do not really have to go through all of these. Each of these little blocks can or does deserve a separate lecture on its own. So let's just reduce it a tiny bit. It's also going to help me a bit. So let's leave these parts to onboard data handling team in Citra, hopefully. And I actually don't like these two, so let's leave them out. No, it's not true. For satellite communications, even though they might be useful, they're not usually super needed. For specific cases, sure, but let's discuss that maybe on another lecture. And synchronization, even though required between the transmitting and receiving system, I don't actually like it, so let's forget about that as well. Okay, so this is going to be our communication diagram. Let's try to get through it really quickly. So first of all, let's go through channel coding. In this case, signal or any sort of data can be represented in a bit form. That can be also represented by a signal, represented by a voltage, for example, shifting voltage. So zeros are represented by some value around 0, and ones are represented by value somewhere around 5 volts. Sure, this can be done, fine. But this information, as it's being transferred, because of some reasons I'm going to list later on, it can get distorted somehow. So let's say that all these bits in gray are going to get distorted, or, well, flipped in this case. So it's going to be the exact opposite. Now let's look into this a bit deeper. So we distinguish 2 types of errors when it comes to these bit sequences we are trying to send. We have singular errors, where 1 bit gets flipped or does not get received properly, and then burst errors, where multiple bits are incorrect. We need to somehow deal with this, else our data is going to be corrupted. So what we're actually doing is we're using special codes. Now, that can get quite complex, so let's keep it simple again. Detection codes, they detect these mistakes, right? And then we can somehow ask, or we can request another message transmission to hopefully receive the data correctly. Or then we can go for correction codes, which are something like magic to me. I'm going to try to explain, but I'm going to try to keep it simple. So these are forward error correcting codes. These codes not only find these mistakes, or sorry, not only detect them, but they also find them and correct them. Now, that's really magic. However, all you have to remember from this part is that codes or channel coding is defined by coding rate. So it's some sort of a ratio of bits coming inside of this mysterious channel coder, and bits coming out of it. So imagine we have 4 bits coming in and 7 bits coming out. Fine, that's all good. So somewhere along the way, 3 bits were added to this signal. These bits are going to help us to detect these mistakes now. Let's have a message or input bit sequence. So this is what we want to somehow transmit. This is going to be our input. So these bits can be represented by these letters. So M3, M5, M7. So output is going to be the same. These bits are not going to change. However, some more bits are going to be added. Now how? By using this. Remember I said there was no math? I was lying. No, it's going to be simple. So let's go. We do not really have to deal with this. This is an equation, fine, or well, matrix definition. We can somehow derive these simple linear equations from that. And we know all these bits. It doesn't really matter what it means, but okay, we know all these bits. So let's actually insert these bits. So M3, this one is going to be here, and so on. So let's add them up. And we see that we finally get all these unknown bits. Now, what is that for? Great. I have all that, so I have all these bits, so let's insert them in. Great. Fine. I have this output message. Now, that's all good. Let's try to corrupt one bit. This one, right there. Okay. Let's use the matrix again. Now, after matrix multiplication, we are going to obtain this. This is some sort of value that is going to tell us where the mistake is. And if we were to translate it to decimal, that is equal to 3. And our mistake is at the 3rd position. So not only we know that there is a mistake, but we know the position where the mistake is. So we can correct it. Of course, there are much more complex codes, much serious math, but I wouldn't like to complicate things. This is wonderful stuff, so let's keep it that way. Now, another concept is interleaving. Those correction codes, those I listed before, those are great at fixing like small group of mistakes or just singular bits, but they're not great at bursts. So if a message gets corrupted and there is a lot of burst errors, then it might be problematic for those codes to detect and correct, of course, those mistakes. So what we do is interleaving. This right here can be viewed as a bit sequence. Those numbers are not necessary. It's just a reference so we know that this position comes here and the first bit in that sequence is going to go here. So we write these bits into some sort of a register down here and we read them out this way. So the opposite way as they were written. We are going to get another bit stream. We are going to basically mix this data up. After receiving some burst errors, we can then somehow untie this bit sequence the same way basically. Now we are going to shift these bits in this way and read them out this way. This part is at the receiver, this is at the transmitter. This is the transmission channel. The received sequence is still going to have those mistakes. However, they are going to be spread out and they're not going to be as a singular group that is impossible to then deal with. Okay, so channel coding done. Let's go further. Okay, so basement modulation. In this case, I'm going to be very quick because I don't like this part either. When we are interpreting bits, we somehow need to signal these bits via transmission line. So we can send pulses, but these pulses are not great. First of all, we cannot really generate an ideal pulse of infinitely small width and super high amplitude. That's not really possible for our systems. What it also does is, after Fourier transform, this is the frequency spectrum. It basically has all the frequency components available to achieve this. This is not possible for our systems to handle. So what we do is we can send pulses, but these pulses are not going to be so sharp. Instead, these are going to be like small little hills or, well, voltage fluctuations in this case. So here we go. First bit was sent. Of course, it can be somehow received. However, we want to somehow, along the line, sample the signal so we know which type or which bits were sent out. So we define some sampling intervals where we investigate what kind of bit is being sent out. So here, it is 1, right? Here, it is 0, 0, 0, 0. So this sequence has been sent out properly. So these orange dots are the points of investigation, and here it somehow equals to 0. Fine. However, if you have longer and much more complex sequences, what can happen is then these small, I would like to call them system responses that basically it is basically a signal that is being sent. That's it. If this little wave is basically too wide and also somehow goes through the point of investigation at this position right here, it is actually going to be added up with another signal. So in this case, yes, we are still going to receive the same sequence. We can somehow estimate like this is 1, this can be 0, 1, 1, sure. Here, let's say it's 0 again, for example. It doesn't matter. In more complex systems, this wouldn't work. This would be extremely distorted, and basically we would not get enough information. So some smart person came up with a sort of a filter. I'm not going to go into filters now. Let's say that we can ensure that the response of a system, whether on a bit of value 1 or 0, is going to be something like this. So instead of that little small hill that goes up and down, we get this. What it does is if we send bit sequence of 1s, this is just an example, and we use this impulse response of the system, we can still receive all these bits. Now how? Well, if we sample at specific configuration, we can see that in the point of investigation, only this signal matters. The rest of these signals are equal to 0 in these points. It doesn't really matter what happens here. Yes, they are going to be summed up and it is going to get distorted. But in this point, only thing that matters is this signal right here. So we can actually receive these bits quite quickly. So baseband modulation, this is how it's done. We can have bits represented by 1s and -1s. These are going to be 1s. These are going to be 0s in this case. It's not worth it to represent these by 0 amplitude, as that would be basically not knowing whether the signal is being sent or whether the line is dead, right? So this is what we are actually going to get at the output. Now, it's a bit delayed, but I can actually see all those required bits, 1, 1, 1, 0, 0, 1, 0. It's still there. The information is there, even though it's distorted. We know how to somehow get it back. Okay, that's it. Now, for passband modulations. Well, let's say that we can effectively transmit this signal via a baseband, right? So low frequencies. However, these low frequencies are not suitable for our basic environment, for our transmission via free space. Why is that? Well, those really low frequency signals, they would be really required to transmit or transfer to electromagnetic waves, because in antennas we're going to see that the length of the antenna is proportional to the frequency in some way. So small frequencies would require extremely large antennas. Okay, so here we go. We can actually use another signal to somehow move the signal from the baseband to higher frequencies. In this way, we can, let's make an analogy here. Let's say that we have a paper with a message. If we throw this paper, it is not going to go far. But if we took a rock, which is going to be our carrier rock, and wrap the paper around and threw that, please don't do that, but yeah, that's a good analogy, that carrier is going to ensure that the signal is going to travel further. So these are the types of modulation. Most important are digital ones. Those are used in space communications as well. So analog modulations, not really required. I just wanted to show them. Okay, so in this case, we have digital modulations. We can actually see that, well, they're called shift keyings, but they're modulations. So here, amplitude varies. So 0 bits are represented by amplitude of 0, 1 are represented of higher amplitude. Frequency, basically, this is smaller frequency, higher frequency. So number 1, bits with 1s are represented with higher frequencies. Here, just different phase. Good. Now, here are some exemplar modulations. You can just view them. It's not really required for anything, but these you're going to actually see in space apps. So these modulations can be somehow represented to be viewed properly once again. So this is somehow we deform space to somehow assess the effectivity of the modulation. In this case, if we have the basic BPSK, so phase shift keying, it can be represented such as this. So we have bit 0 with 0 phase shift. Here, I can be sort of representing, for example, phase, right? It doesn't really matter. And after phase shift of 180 degrees, the other bit is going to be represented here. So after reception, we can this way assess which bit we are actually getting, whether it's 0 or 1. It doesn't really matter how to view this. It's again a tool that helps us to distinguish between the data being transferred. We have higher term modulations as well. These then look something like this. So in this case, we are not sending only bits, but actually groups of bits, so symbols. And then we have more complex modulations, which take on specific physical properties, which are very advantageous to us, and that's 16 QAM. So this is how it looks, and it allows us to transfer even more data. So that was passband modulation. So for antennas, we already know how this works. We explained this concept. However, for antennas, it's, again, a bit more complicated. Let's try to get through it a bit quickly. So let's say that we have this piece of iron. Well, it is our antenna, dipole in this case. Let's represent it like this. So it's an open line. It doesn't really matter. But these antennas, they basically serve as a intermediate between the transmission line, which the signal is traveling through, and the free space. And by this configuration, it works better. So the antenna length is related to frequency in this way. So wavelength of the wave divided by 2, if it's equal to the antenna length, there is the antenna is as efficient as possible, basically what it says. So that's why we cannot have small antennas for extremely slow signals around 1 Hertz, because that wouldn't give us any efficiency of the signal transfer to the environment, basically. So for antennas, we have some parameters. Let's quickly go through these. So antenna has some sort of a radiation pattern. If we have a point source, we're going to have a radiation pattern that is going to be basically omnidirectional. But we can configure these antennas to be directional. That means they send signal in a specific direction. We have antenna gain. Antenna gain is a parameter that somehow is related to direction. And what it does, what it tells us, is that how much gain or how much power does the antenna concentrate to a specific point. So in this case, anywhere around this globe, if we were to choose a point, the gain would be the same, because this point antenna radiates into all directions. But this one right here is quite directional into this point. So if we were to study gain here, compared to this antenna, it would be much higher. It is usually the gain, the parameter is related to some isotropic idealized antenna of choice. Okay, antenna types. If we're talking about space, you're going to see these. So I just wanted to mention a couple of these. So for each band, there is different antennas used. Why is that? Well, signal likes to sort of transform into free environment by basically signal wants to be transformed to the free space environment in a way that sometimes another type of antenna configuration fits better the cause, right? So in this case, this is the same antenna. We have these beams similar to the dipole I showed earlier. This is a patch. It's basically some sort of a resonator that transforms the transmission line signal once again to free space. This is a bunch of them in an array, and then you can have also antenna dishes of sorts. So, good. And that should be it for now. So, yes, so we actually went through all these different sections at the top. However, there is still transmission channel left, and then, of course, the opposite receiving side. However, the receiving side can be viewed as exact opposite of what I've been doing here today. So the transmission channel characteristic has to be left for another SpaceBeer, unfortunately, because we're running out of time. So I would like to invite my colleague here to also present, just partially, a presentation about his trip to ESA Academy he managed to absolve quite recently. So thank you very much. This is going to be all from me. I would say 10 minutes. Yep, sure.
So hi all. I will have the second presentation about the satellite communication system and my experience in ESA Academy. My name is Alex, and I am student of space applications. Currently, I'm working in Czech Aerospace Research Center as a research and development assistant. I am also the member of the YSpace as the member of communication group. And as I mentioned, I was a participant in a satellite communication system training course at ESA Academy in Belgium. I love space, I love nature, and I like music. Very particular part of music. So the content of the presentation will be ESA Academy experience, and then some introduction, history, principles, and applications of SATCOM systems. And at the end, possibly no beer break, because I hope that my presentation will be short and the next speaker will continue. Okay, so I had the opportunity to, I was chosen to be a participant of this ESA Academy course about satellite communication systems. We were 30 students of master's and PhD programs from 30 EU countries. All the other participants were amazing, and it was probably one of the best weeks of my life. And the topics of the course were telecommunication payloads, so antenna and some communication equipment, operation, ground segments, about security, and then some non-technical parts like legal aspects of communications and economics of the telecommunication segment. And if somebody is interested in communications, there will be in February the Lady Bird Guide to Spacecraft Communication Training course, and the deadline to apply is 11 December 2023. So I think 1 week or less than 1 week. And if you are not interested in communication, then you can check the link, and there will probably be any course, because it's a very broad spectrum of the fields which they cover. So, okay. Now let's start with SATCOM systems. The main principle of the satellite communication is to use artificial satellites on the orbit of Earth, or later Mars or Moon, because there is a new space race for Moon, to relay data between place A and place B. So if it's only on orbit of Earth, between some places at Earth, or between celestial bodies. It uses RF mainly for communication between satellite and end-user terminal. Opticals are now mainly used for inter-satellite links, but they are also having breakthrough also in the end-user terminals, and some hybrid technology which combines the two together, and it's applied mainly when there are cloudy days. So when optical communication isn't possible, then RF is as a redundancy. So now the question for a beer. Do somebody know the name of the science fiction author who defined the first use of geostationary satellites? Who was it? I don't know. Who said that? Okay. You have a beer. It was in the year 1945. And he proposed that with the 3 satellites on geostationary orbit, it will be possible to cover and create the communication between global coverage between any points on the Earth, and to relay the data between them. Some years later, in 1957, there was Sputnik. It has the broadcast of radio signal, so everybody was able to listen to its beeping in the normal radio. So it was also some first communication satellite, but only as a broadcast. Then there was first US satellite, Explorer 1, and in the same year, in December, they released or launched the first purely communication satellite, SCORE. And it was first really primarily focused communication satellite, so for data relaying. Then, in the year 1962, there was the first telecommunication satellite that allowed the transatlantic television broadcast. It was Telstar 1, created by USA. 2 years later, Syncom-3, it was first geostationary satellite, and it was used to transmit the Tokyo Olympics at the 1/3 of the Earth. So now some graphics. Basic description of communication system. So between two satellites, as David said, there are inter-satellite links. They are a little too complicated, so we are not going to tell more about them. There is between satellite control center, which is like really controlling the platform of the satellites, so where the payload, so antennas and communication gadgets are placed. It controls mainly that. And there is a gateway or hub, which is used to translate the data from air or space to the network. There are forward link from gateway to users, then return link from users to gateway, and there is also gateway link between satellite and gateway, user links between satellites and any users, and also there are mesh links, which are the communications between different users through satellites without any interaction with gateway. So, pros of the satellite system communications. They are ubiquitous, which means in Czech všade prítomný, so possible to communicate in all places, because when they are correctly designed, the constellations, there is really the possibility to communicate from any place on the Earth, any remote, because the terrestrial links have problem with when there is problem with missing the terrestrial infrastructure. And they are more resilient to physical damage, because, for example, we have the situation in Ukraine, and when the Russian army came, they destroyed the terrestrial infrastructure, and if there was no satellite communications, there will be nothing, no communications. So they are now used together with terrestrial networks to make the communications more resilient to damage or destruction. But cons are that there is higher latency with altitude, and the usage of power is also higher than in terrestrial networks. Main use of communication or applications of satellite communications are fixed or mobile service, so for sea, for airplanes, or for land, mainly the army usage, but also the Wi-Fi connection at the airport, the airplane, or something like that. And the main constellations, most popular constellations are Iridium and Globalstar, which are used for mobile communications. Interesting thing is that both of these, both of companies that created these constellations have bankruptcy in their history. So it is really hard to create the constellation from financial standpoint, because it's really financially hard to transport the whole constellation and make it really profitable. With the rise of Internet of Things applications, there are new researches and applications for direct and indirect, which direct are from device to gateway, which is satellite, or indirect, which are from device to ground gateway and then to satellite. Other applications are TV broadcasts, but with the decrease of watching TV nowadays, it's a slightly decreasing field, but it is still like, I think, 60% of total income or finances in satellite communications. There is also broadband or internet coverage, which is very popular now. I think everybody knows Starlink or OneWeb or these things, or Project Kuiper from Amazon. And also the main purpose, data relay constellations for governments, for universities, for army, for everybody. the main concepts about orbit are that on LEO, there are needed more satellites in hundreds or thousands, but the latency is really small in comparison with geosatellites, which have like a half of a second. So if somebody wants to play the game through satellites, no geo, because it will be hard, mainly in first-person shooters. Geo have the pro that it is always over horizon, and LEO satellites are like they have a very short time of passage above the horizon because of the lower orbital height, and medium Earth orbit satellites are somewhere in between. But nowadays are really popular to create multi-orbit constellations, so really connecting all the pros of the orbits and trying to get rid of these negatives. And also multi-layer networks, which are the connections of terrestrial networks and non-terrestrial networks, so the satellites. There is also a significant rise in LEO broadband mega constellations like Starlink or Kuiper, which I mentioned. And there is also a very big emphasis on building whole ecosystems or service merging. So, for example, as Amazon have this cloud services and these things, they are now adding satellite communication. So you can collect the data from IoT device through satellites to their cloud systems. So really one big ecosystem. And also many terrestrial mobile operators are now trying to make breakthrough in satellite communications. Shortly about payload. So there are antennas for these satellites, which are used for receiving and transmitting of signals with selective coverage, which are created by beamforming techniques, but they are for whole like 2-hour presentation, I think. So it is really complicated. And also communication equipment like filtering, so getting rid of frequencies we don't want, frequency mixing, because if we receive the signal at the one frequency and we transmit it with the same frequency, then we will have feedback and it will just make noise really bad. And also there are amplifying of signals which are separated in individual smaller bands, because like amplifiers with 20 kilowatts, which is the power of nowadays satellite system, is really complicated. And it's end. So thank you for listening.
Shall we make a pause or we continue?
Okay.
Okay.
Jak se páči?
Také jsem. Top gear. Does it work?
Yeah, it works. Great.
Jiří tu bude mimo. Takhle. Okay.
Okay, so he kinda caught me out of the guard with the sudden end, so I didn't have the mental time to prepare. Also, we have a really small amount of time, so I will take it as a speed run. I hope everyone is okay with it. If you are more interested in the topic, come after me after the presentation and I will tell you more about it, yeah? But yeah, I'm Jiří Veverka. I'm also a student of the space applications, and I'm also a part of the YSpace. I'm there as a, they say that I'm software lead, so let's say I also work at Honeywell on microcontrollers on aircrafts, so I use some experience from this field into the space as well.
this is basically what I wanted to talk about today, but since we are in time press, as I already mentioned, I will skip maybe some of those. Yeah, so let's start with the history of software. First usage of software in the space was basically at the Mercury Atlas mission. Of course, they used it before, but the first big usage was in those missions. It was used mainly to maintain the altitude and to control the spacecraft. It was on the IBM computers, and it was in the early 60s. By the way, does anyone of you know what was exactly the Mercury Atlas 6 mission? No? Oh, you know?
Yep, first man mission.
It was the first man on the orbit that was not ballistical. So it was John Glenn. You can see the correct picture of him getting into the aircraft or into the module. And this is how it looked like when it landed. The computer itself was located in this part. Yeah, that's basically all of it. Then at the end of the 60s, there came all-known Apollo mission. They made it to the moon, so I hope you know it. And this woman, you can see here, there, she was the lead engineer of software for the Apollo mission. And the code, the books you see besides her, it's actually all code handwritten by her. They also included many Easter eggs in the code I will show later. But let's move a little faster from that to the Space Shuttle program. Those two first programs, they had just the basic control of the system, the navigation, and so on. But here, except the Apollo program, they had to think about the navigation to the moon and back, landing on the moon, and so on. Here, we have already more complex things like complex maneuvering, the safety of the crew, because they have to live somehow up there. Yeah? The manipulation of the big arm they had at the Space Shuttle, if you know what I mean, and also some subsystems like communication, battery management, like on the big whole system, the propellant, and so on. Here should be this is the Easter eggs I talked about. When they wrote the code, they actually inserted some funny things inside. For example, here, this is the code that was used to land the moon lander on the moon. So when the landing sequence was initiated, they marked it like, okay, let's go see the wizard. From the Alice in the Wonderland, I hope you know. Also, there are many things that they were trying to talk about. Why do we need software? Well, as in last or one before presentation was told that electric system is the heart of the satellite. The same can be said for the software, but it's the brain of the satellite. Without it, nothing would happen. So we need it. And we need it usually in the critical way. So we need to be sure that the application works as it's intended. It doesn't stop working, or if there is some kind of fault, it's able to work with it and overcome it. And I will talk more about it later here, but there are multiple ways how to ensure that it will work even though there is an error. Also for the code, for the critical applications, we have something that's called standards or guidelines. I will also talk about it later. And usually we need it for everything that you can imagine, communication systems, the battery management, so you know how much power you have left, so you can let your satellite on, for example, sleep mode, if you have not enough battery, so if you are in the eclipse, so you have no sun, navigation, data processing, or algorithms, as my colleague Rado Pitoňák will say later. Let's move. Nowadays, we have some processors, because this is embedded. So we are not working only with software, we are working also with hardware. So we have already some flight-proven processors and hardware that has been already used. For example, the AVR that are really not powerful microcontrollers, through the MSP and Cortex series, up to the more powerful processors like PowerPC and so on that can run full operating systems like Linux. Let me focus on those two, MSP and Cortex, because those are those two that are most used in the missions nowadays. When we try to work with them, we usually work with something that's called RTOS. You can imagine it that it's like your operating system. You log into Windows, you play videos, you play games, you look on YouTube on something all in one time. That's usually not possible on those microcontrollers because they are too weak for it. So there is some go-around that's called RTOS that you can use to make everything you need on the orbit. ESA used RTEMS. That's already pre-certified, so if you use it, you don't have to care about too many things from the standards because it's already been done. The same can be said for the Safe RTOS. That's the NASA version of it, but it's pricey, it's proprietary, you have to pay for it. So the next step, if you don't want to use any of it, is to use just the free version. It's open source, so you can just open it and edit it. The details how to edit it, if you want to know it, I will tell you separately, not now. But yeah, even though if you use it, you have to comply with the high requirements for the safety, for the critical systems, and for the functions. Sorry. Yeah, for the functions. If you decide that you don't want to use it, you can always implement your own system, but that's too costly, that's too time-consuming, and usually, if you're not following any guidance, you will find out yourself in a dead end because you don't know how to communicate with the regulators on their side, how to explain to them that, but man, this works like how it was intended to. You have to stick to the standards as the best as you can. The next thing that's widely used in the space software is something called CubeSats space protocol. Okay, now thing I should mention is that I'm mainly talking about the CubeSats. This is a wonderful thing because it enables you to decentralize all the components in the system, that communication acts as its own computer, the payload acts as its own computer, and so on. And nothing is tied down to one computer only. Everything acts independently, and then it communicates with only the one main thing, that's the computer, the main computer, the OBC. If you are familiar with the networks, it's on the layers L3 and L4 of the OSI-ISO model. Nice thing about it is also that it's open source, so it's community supported, and many manufacturers, they use it to include it by default into their components. So when you buy it, you can already plug it in with not too much tinkering with it. So it should work like that, yeah, if you use this, and if they use it as well. Standards and guidelines. I already told you why we need them, but what are the other reasons? Well, we need to have a clean code, because when, for example, I leave my job and someone else takes it over, he needs to know where I ended, what I did. So we need to standardize those things that I write so other person can understand it pretty quickly. The other thing is that they declare how to lead the review processes so the code quality can be assured, even though we may know almost nothing about the principles of the programming language itself, because the standards, they just tell you, use this, don't use this. You can do it. Yeah, and also we can press reset button in orbit, because if something goes wrong, you can go there, you can repair it on spot. You have to rely that it will work or you're screwed. For this, those standards are usually from the ECSS, that's ESA. NASA has its own standard as well, or RTCDO. That's something I will tell you about later. That's pretty interesting. those are the general standards, and for the standards on the code side, we have MISRA C, JPL coding standards. That's those standards that tell us how the code should be formatted, how it should look like. So you know what you're doing. The RTCDO is a little imposter in here, because it's actually a standard for aircrafts, not for space. But many things are really, really similar. They have many things in common with those two. So I included it so you know that you can use it as well. Just take out the part about living people on board and so on, because you have no people there, right? And if you do, there's something wrong with you, man. But yeah, we've got through all of this, and now we are in the part that we've got assembled our system. We come to the certification authority, and we are like, okay, I've got this part, this part, and this part. I want to certify it, but I've got also some other parts that I do not want certified. Why? Because I already certified it in some other mission, and I'm reusing it, or I already bought some pre-certified component from a manufacturer, and I can use it as it is. I just have to say the certification authority, hey, look at this, I've got documents, it's certified, you can use it like that. There is also a fourth option, which says that if you have something that's on the same level as those standards, you can use it as well, but you have to prove it that your standards are on the same level. Development process. Yeah, that's the part I wanted to skip. But let's take it fast. Usually we have some team. We have a team when we are working together, and we need to have a process in which we are going to guide the development from start to the end. Among many others, nowadays the test-driven development is on rise because it helps you to save time in development, and you do many things at once. You can see it in here. You get requests from customer or from system engineer to program. So you make immediately a test. The test immediately falls because you don't have any code. So then you write the code passes the test, then you make some adjustments to the code so it's clean, it's according to the standards, and then you can say, okay, I'm done. Or you can iterate if it's not okay. We've got also another modes of development, let's say, processes, but let's keep them. And this is the last part before the break, testing. This is basically the most important thing about development. Around 40 to 50% of development takes the testing. And not just testing of the code itself, but testing of the requirements on the static level. It means that you just read the document, and by your own logical mind, you say, okay, this makes sense, okay, this doesn't make sense. And you go through that. And also through the code, and also through the statical code. So you take the code, and statically, again, using your mind, you go and, okay, this line of code makes sense, okay, this is completely bullshit. Don't use it. You do it. The means of testing, you can use simulations, so you can simulate the various conditions in the space. It's pretty harsh there, so you can use it. Or you can use some big test tracks. You have, for example, radiation test track, so you can fire some particles on it and then evaluate if it changes something about the hardware or not. You can make some code analysis like static, not like that you are looking on them, but you're already using some tool, for example, lint, if you know. You can have some development stations that you are basically having by yourself that are not the entire satellite, but it has the main components of it, and you are uploading the code on it and testing if it works as it should, at least on the ground. And yeah, and emulators, if you have neither of those components, I don't know, you have no money or the manufacturer didn't have any time to make it, you can always emulate it. That's basically a program that simulates your hardware. You can do it on it. And I believe we have now a pause, beer time. Yes, this cute little duck. So take, I don't know, 5, 10 minutes? 10? It's okay? Okay, 10 minutes. So in 40, we will start again. everything clear up until now? No. No? Okay, I will kick you outside, okay? Okay, so let's move the little Q duck. Data generation. So data on our satellite can be acquired in multiple ways. The most common way, as the primary way, is usually the payload. It's the thing we have in our mission that we are usually studying or making use of it. Yeah, I believe you know what's payload. The secondary are OBC, so our computer tells us that maybe something's not quite right at the moment with it, so some information, some logging, or some comments from the Earth, what to do with the satellite. That's the data we acquire, and we have to process them. Some example about the data acquisition. Oh, okay, sorry, I skipped. You can see the diagram of data acquisition in here. In the middle is the flight computer, and on the sides you have multiple peripherals that are generating the data that are going inside or outside the computer. For example, outside to the communication system that's sending the data back to the Earth or to another satellite. It depends. Example of it is, let's say, the RAX mission. It's a mission that's supposed to monitor the large plasma clusters in the ionosphere. It's because we needed to study how it interferes with the signals that are coming out and into the Earth from the space. It looks like this, the data. This is actually data that was taken above the Alaska. This is how the northern light, aurora borealis, looks like on the spectrograph. Another thing how we can move the data is using multiple buses. Bus is a hardware-software definition of, you can imagine it as a highway for data. And we have multiple ways how to transfer the data. For example, CAN. CAN was actually invited for usage in the automotive, but now it finds more and more usage in space. So it's really robust system that we are now using. The second most used is the I2C bus, but it has one little problem. When we are in space, we can encounter some interferences, some electromagnetic interferences. So how to cope with it is we make dual or differential I2C, which you can see here. Oh, I have not updated my presentation, sorry. But basically, if you get the same interference at the same time, it will differentiate as 0, and you get nothing. But if there's a signal in between those, you will get the signal as clear. We are supposing that the interference happens equal on both lines, so those lines have to be as close as possible. There are some other buses, for example, SpaceBeer, Serial, and SPI, Ethernet. Those last two are not often used in space, so we can skip them. Here is a nice picture of how the diagram of the communication looks like. You've got some modules here, and those modules communicate with the main computer on those buses. So I2², GPIO, I believe there is, I can see it, sorry, and so on. Then we need to monitor everything that happens in the space on our satellite. It doesn't matter if it's because of errors that can happen, or if it's because that we've got some data that we haven't got any track of, or that we've got some communication that was incomplete. We need to check and log everything that has happened, so we can fix it later if there's a problem. The other thing is that if we've got some problem with the satellite, we need to check it if there's a problem or not. So for example, when we start a satellite, we need to check if the memory of the satellite where the program is stored is okay. We usually do it by some CRC, that's a polynomial thing. You check if everything is okay, or if the checksum, that's some value stored somewhere in the memory, if it's what we expected it to be. We can do it also on data that are coming or incoming out of our satellite. So we can check the integrity, or if the program that we are currently trying to load, let's say we are updating our system, we are trying to see if everything has come correctly as it needed to come, because you can get corrupted, and that's pretty bad. But I will talk about it later. We can also use some fault-preventing algorithms or method. The most used is the var leveling. Basically, every memory has its time life. And when you use the memory like, okay, let's put the data there, just put it, and we don't care how, it can happen that we will wear out some regions more often than the others, and then they will become unusable. So there is an algorithm that checks the memory regions that were the least used, and then we store the data on them. So we use all the memory regions equally. We've got some types of errors that can happen: logic errors, algorithm errors, or errors that can happen because of the harsh environment. So for example, some ionized particle comes through our computer or some memory part, and it corrupts the data. For example, it can switch the bit from 0 to 1, or vice versa, and that can be a problem. Luckily, as I said before, there are mechanisms to check it, CRC, checksums, and so on, so we are already prepared for it. Or we can have a problem that's called single event upset, latch up, that's when the same ionized particle comes through a transistor and it changes its logic function, let's say. So it behaves unnaturally of what we want it to behave like. Another thing, we can prevent failures in our system, in our satellite, is that we make everything redundant. So for example, we make two computers, and if one of them is out of service, we just boot the another one. Or we have two softwares on one computer, but on two different memory regions, and if one of them is corrupted, for example, from the single event upset, or if something goes bad with the upgrading with the system, we can check it, and we can switch to the working one. With the redundant system, there is a little bit problem that comes. If you make it wrong, it can be actually worse than if it wouldn't be there. So you have to take care of it properly. Also, we have something that's called multi-level watchdogs. That's something that checks all your systems regularly, and if there's an error, it resets the whole system. It's best to implement it on the hardware level, but we can do it on the software as well. Here you can see a drawing on how it looks like when you're starting the computer. Bootloader is the core of the program, and then it decides if it will start the program number 1 or program number 2, decides on multiple levels if there's error, corruption, and so on. Oh yeah, we can skip this. We can skip this as well, because Rado will tell us about it more later. Communications and security. Yeah, as the guy said, communications can happen between Earth and orbit, between satellites on orbit, one to multiple. We've got clusters, for example, Starlink. So every single one of those communicate with each other. That is basically the easiest example that you can think of and use it. But also, in communication, we need to take care of security. So if you have unsecured communication, someone who is a little bit skilled in the communication can come and say, okay, I see this communication, I will send some malicious commands, and I will send your satellite into the atmosphere, I will destroy it. We don't want that to happen. So we need to encrypt it, we need to secure it, we need to encode it, everything that we can do. But that itself, it's on one whole another presentation, so let's go not too deep into it. And since I said this is speedrun, this is my last slide. Update and maintenance. When you have your satellite in the orbit, you have to take care of it. And you usually do it by sending some comments, you check on the health, you check the logs, what it said, you update it if you find some inconsistency in the program or something that you haven't used before, but you found out that, oh, okay, I can use it. We update the software. We do it, we need 3 things on the basics to ensure that it happens. First, we need to have enough, we need to have big enough the communication window throughout which we can send the program up. Because if we are on different orbits, let's say we are on the planet in here, and the satellite is here, we can't communicate with it. But when it goes around and we are again in here, we are in the communication window when we can communicate with it, so we can send him the commands, we can send him the updates and everything. But we need to be careful, because if we do it in an unorganized way, we can actually destroy the system if we have no fault protection. So, for example, we need to compress the program and send it as a whole in one big sequence, or we need to keep a track of the data of the packets that has come. And when we are at another revolution, we need to send from the satellite a request for another data to fill up the rest of the missing program. And like that, we step by step flash or program our satellite to the new version. You can see it somehow here. When we start our satellite, we're on the version 1. Then we start uploading, but the satellite goes off the window when we can upload it, so it still runs on the version 1. The version 2 is corrupted, we can't start it, we see it's corrupted. But on the second revolution, when everything is done correctly, when everything is uploaded, we can say, okay, this checks, the checksums, the CRCs, everything is right, it works. We can boot from it, we can start the new version of the program. And that's basically everything from me for today. I hope it was not too speed run. I hope you understand. Next will come Rado from Zajtra. He will tell something more about the AI and algorithms. And if you're interested in knowing more about what I just said, just come to me and ask. Thank you.
So I think we can start. Somebody's taking a beer, so it's okay. So hello everyone. I will just continue on the same topic as the previous speaker. So my name is Rado Pitoňák. I'm from Zajtra. I'm the only one probably not here from YSpace, so I'm sorry for that. Hopefully they will invite me after this session. So I will talk more about the specific part of onboard data handling, which is onboard data processing. I will maybe first say what we do at Zajtra, and we have this short sentence that we optimize space data delivery by providing onboard data processing products and services. I will talk more about it on the next slide. But so I would start with this question, like why to use onboard data processing. Before, in these two presentations, we were talking more about the model of acquiring some data in orbit and send them to the ground and process them there. We want to shift this a little bit. First, maybe I will explain why this word data, because, and this is the important part for us, that satellites are built around the payloads. So the payloads are what's like the most important thing on the mission, not the satellite itself. The satellite itself is just there to support this data collection from the payload. And why it's important for us, this onboard part, is that these payloads typically in these modern missions collect more data that we can transmit to the ground. So we will never can downlink all the data that this satellite, especially CubeSats, are collecting or are able to collect. So if we can process them on board, we can get some maybe insights that would be lost otherwise if we haven't have this. So how onboard data processing can help here? So I have three, let's say, added values that we can provide if we process this data on board. First one is that we can filter out unusable data already on board. What does it mean? The best example that I can give is Earth observation. And in Earth observation, especially this is regarding the optical missions. We can have like a radar mission where it doesn't matter if we have clouds, but typically 67% of Earth is covered by clouds. So, and clouds are really like unusable data for us if we don't want to study clouds. But if we want to study Earth or Earth's surface, the clouds are unusable data. So we can utilize something like cloud filtering already on board. So identify either what's the cloud percentage on the image already on board, or we can actually like have some mask and send just pixels that are not cloudy back to the ground. And here we can save a lot of downlink. You can imagine if Earth is covered 67% by clouds, we can achieve like a high percentage of saved downlink if we can identify this in orbit. But it's not just clouds. We can have also some scientific missions. For example, we were working on a Slavia mission, that is a mission for meteor detection. And these are the events that does not happen like much, or most, if we have like a camera turned on continuously, most of the data will be not usable for this scientific goal, or we cannot transmit all of the data. So we need to somehow select which parts of data are like interesting for us. And so we were preparing a design of the system that would on board identify meteors passing the atmosphere and take just the part of the video or the sequence that contains or has high probability of containing meteors. So this was regarding the first thing, so filter unusable data, focus more on the data that are with added value. The second thing where we can see added value of processing data on board is reduce latency for retrieving usually like time critical information. What it can be, like imagine wildfires detection. If we have like a traditional pipeline, we just camera collects the data, data are then scheduled for transmitting, we send it to the ground, pre-process it, and then some people analyze it on the ground and find that there is a wildfire. But if we can skip all these steps, that can take like hours or days, and we can just right after we take some picture, that we are able to detect the wildfire and send to the ground just the information regarding the approximate location, we can really reduce the latency of the information. So this is another use case we can solve by processing data already on board. And the third one is to enable onboard autonomy. This is something that is, for us, at least at Zytra, more like long-term thing. The first two we can do already like right now, but the third one will be a hard one, but it's important especially because of the constellations, especially Earth observation constellations, but it can have a huge advantage if we can know more information already on board and, for example, optimize this constellation for some higher level goal. For example, if we want to have as much data from, I don't know, like Europe, we can set some higher level goal as an operator to instruct this constellation to work in this way. And then through inter-satellite links and regarding the data that we gather, we can somehow operate this constellation without or just with supervision of the operator. So this is some long-term goal, but also this technology enables this, that we can have these autonomous operations of constellations. Great, so this was the first part showing like why we should do this. I hope now it's clear why we should do this. Now it's how we are doing it. And this system, previously on the presentation, there was mostly talked about the critical systems. So, for example, onboard software or central software is a critical system that if it fails, we have a problem. If the system for onboard data processing fails, like we can lose some advantage, but we will probably not lose the mission itself. So there is, let's say, we don't have such a high standards for a criticality, so we can experiment with some newest technology. And what enables this to be done is basically that some hardware acceleration is possible in space. And here are a few ways how we can do it. First one is the obvious one, but to use some CPUs. The other ones are FPGA, GPU, probably everybody knows, like graphical processing unit. We can accelerate some computer vision on it. And there are some ASICs, so chips that are made for a specific use case. And they are also utilized in space missions. So I will take them one by one, maybe, and give some details that some of them we can skip, but just for you to know. the most traditional, let's say, way how we can do it is just to use some multi-core CPU. There are some of them listed here. Some of them are especially used at ESA in like ESA missions, and they are something that is called like radiation hardened by design. So they are basically designed so they are resistant to the radiation effects. So here are a list of some of the, let's say, state-of-the-art multi-core CPUs that are able already to run some kind of AI models inference. The other one is to use SoCs that have like a system on a chip containing CPU and FPGA as well. And here are a few of them used in space. I would just highlighted Xilinx Zinc because it's the one we are using at Zytra mostly, and we are optimizing our algorithms to run on the FPGAs from Xilinx. And on the right, there is board that will, the bottom part is actually PCB manufactured or let's say created or designed by us in a cooperation with other company from Brno. Its name is Soltronics. And this board is a carrier board for a module that has a Xilinx FPGA on it. And this will be actually have a space heritage next year. So we are also qualifying some of our software there. So I will talk about it later. Another can be GPUs, and especially the NVIDIA Takes-2. It's if you know Jetson for its NVIDIA embedded GPUs. They have been already used in space, and for example, Satellogic, it's one of the, I think, biggest Earth observation constellation companies, are using it on board of their satellites. So you can basically run AI models on it the same way how you can do it on like your desktop GPU. So with, of course, a little change, but they have a very similar API. And there are some ASICs. Some of them I saw that as a part of ESA project, there were done some tests on Google Coral, but I think it never gained space heritage, as far as I'm concerned. But what is important, or what is interesting, is VPU from Intel, and they use it on FISAD-1. It's a mission from ESA that had so-called like first CubeSat with AI on board, and this is actually the picture of the board that were accelerating the algorithms. And one of the use cases was actually the cloud filtering that I showed before. So the algorithms were filtering clouds already on board. Great. So now I maybe give some insight how to train these models. And for this, we are using, of course, like supervised learning. So one of the important things for us is data. And we have like our own annotation procedure. We use a tool that is called CVAT. It's from Intel as well, I think, and it's open source. And we have like part-time annotators that are annotating the data for us. So we are collecting our own data set. Here is the example that we are also having object detection algorithms. And here is some demo that we were like annotating some objects from panchromatic images. So then the models itself, there was a trend of, I would say, a few years was that the models got bigger and bigger and deeper and deeper. But even now, we come to an age that these giant AI models or these huge AI models, a lot of the people, including Sam Altman, thinks that this era is over. And there is a trend that we want to be able to run these models, for example, locally, accelerate them locally for inference or so on. So we want to actually make these models with the same performance, let's say smaller and having a better performance. And this is actually the challenge what we are doing also on the satellites, that we have their device that is taking a few watts, and we want to deploy AI model that performs the same way as it would run in cloud, where there is a cloud GPU. So we need to optimize it a lot to be able to at least have performance that is comparable with this. And so this is what our main focus in this area is about, that we want models that are very small in size, few megabytes usually, so we are able to easily update them in orbit. And we want them to have very low power consumption overhead, so we don't take a lot of power budget from the satellite. But also we want that they are achieving real-time performance, and they have like negligible accuracy after the deployment to this device. So you can imagine that this is a lot of trade-offs that we need to make, because some of these parameters are going against each other. And last but not least, we want them to generalize well on different sensors. And by sensors, I mean different optical instruments, because we want them to run on RGB data, but also like hyperspectral data, multispectral data, the cameras that are taking other parts of spectrum than the visible ones. So this is another challenge that we are working at, because if you think about the models that are optimized for like smartphone cameras, it's usually RGB data that we are processing. But here we have also the data from other spectrum. So this is another challenge. So how we are doing it, the three things that I will mention here, we are compressing these models. First method is by quantization. So we actually are using lower bit widths for weights and activations. And this can go as low as 1 bit activations or weights. And this is possible thanks just on FPGA, where you can actually implement arbitrary data types. When we are talking about GPUs and CPUs, usually you can go down to 8 bits with some quantization frameworks. So this is the first method. The second one is pruning. So we can actually look at which parameters or connections of the neural net are contributing to the result the most. And the one that contributes the least, we can prune, so remove. And the third one is knowledge distillation. So this is something that we have a large model or a very complex model that is the smaller network is trying to mimic the behavior of this larger model. So these are the three ways how we can compress them. And another thing we are doing is actually not having just one model or few models that works independently, but we are trying to chain them together. So this means that if we have this acquisition, we can split it to the tiles and then perform cloud screening on each tile. And then when we find the tiles that are like polluted with clouds, we can remove them and use, for example, for some other neural net, here is object detection network, just the tiles that have like a small cloud coverage, and then we can get these results and compress them and send it to the ground. So by this, we can actually really extract the added value from the picture, and the final result can be very small because, for example, in this case, we could just send coordinates of the items in the image. Yeah? So, for example, we can send estimated coordinates of the ship in the image, or we can send the metadata information in telemetry. So we can say, here is a picture that contains 100 ships, and then operator can decide, okay, this is the picture I want to download in full quality and inspect it. So we can provide this additional information for operator. So this is how is one of our on-ground scripts look like. So if we get this, for example, full scene with metadata from satellite, we can actually display the information on the ground like this. So here, the scene or tiles that were identified as cloudy, having the more like yellow color, and the ones that don't have cloud coverage are like purple, or I don't know what color is it. And then there is like object detection performed on the rest of the tiles. And if I show the detail of the scene and then the detail of the detail, we can see that there is a like airplane identified that we're flying over the ocean, and we can provide this metadata to the operator, and then he or she can decide if to download this picture is a good idea. So that's everything from my side. I wanted just to be brief because all the previous speakers were promising that it's going to be quick. So hopefully I made it quick. But I will do something different than other speakers, and I will maybe leave time for questions if somebody have any. Can be a stupid one. No question is stupid.
Can you do it in real time, like on a video?
So this is more complicated. For example, cloud screening that I showed, we can perform like one 12 megapixel scene on FPGA, process it in like 1 second. So depends on what would be the frame rate. But when we deploy this model to FPGA, we are close to real-time performance. When we are deploying it on CPU, for example, that's more problematic on the satellite. It's like a few second inference, so definitely not real time. That's why it's helping us to filter some of the tiles that are cloudy and just do object detection on the subset of the images.
Stupid question. How does it work in a hurricane or thunderstorm when everything is cloudy?
So when everything is cloudy, it's like it should identify it as a cloudy scene. So like it should work the same. If or I don't know how you mean this question, because the algorithm is actually like identifying clouds. So if there will be hurricane and everything will be cloudy, it will be just considered as 100% cloudy scene. So
could you still identify like an airplane?
So this probably not. If it will be like under the clouds, we cannot see through clouds, unfortunately. So yeah, we cannot. So this scene would be probably considered as cloudy, and nobody would like to. Yeah. Thanks for the question.
Do you have any means how to recognize whether it is cloud or wave, for example?
Or what?
Or wave. So if you are performing air observation over the ocean, there must be ways which are pretty much similar to the clouds.
Yes, there is a lot of things that can be pretty much similar as clouds. For example, snow. Here, it depends on what data then we have. If we have like multispectral data, it's some added information to it. If we have just RGB data, it's hard to say this is cloud, this is snow. There is a lot of false positives in this case. With the waves, this depends on the data that we have in training. So can be false positive. Yeah, this can be problematic for the network. There is a lot of examples that looks like clouds.
Is it usual to use some strong compression to transform the data? Because you can use some hardware acceleration for strong compression. So is it often to use in this case?
Yes, we can. We are doing this. Right now, in our payloads, we are utilizing a compression just in the software part, so it's running on the CPU, actually. But we have some, we know some compressions that are accelerated on FPGA, but this will take us the space on FPGA. But yeah, there are compression specifically suited for Earth observation, since they are using the advantage of having like more bands, and you can compress. If you have a good aligned bands, you can like increase the compression a lot. Yes, this is definitely possible to accelerate compression. But we are doing it just in software right now.
A bit stupid question. How does it behave when there's a plane over the clouds? Because there will be like 99% clouds, but maybe we still want to identify the plane?
Yeah, this is a good question. Yeah, this will probably not work. Yeah, the scene will probably be like considered cloudy and will not go for further inspection. So, but it's something that would really suffer the performance if we would do object detection on every tile. So this is something that we need to like have a trade-off over. But it's a good question.
When you said it would go under the further inspection, the inspection is done manually, or do you have some algorithms that are doing it?
On like in orbit, this is automatic. So if we
the case with the plane.
So the case with the plane, the scene would be considered cloudy and will not like go further in the pipeline.
Okay.
Yeah. But the inspection, if you mean like the metadata inspection that is transmitted to ground, this is done by the operator. So there is like a list. These are the scenes taken on the last pass, and this is their cloud coverage, and this is the objects identified in them. And the operator can decide if he wants to prioritize some of the pictures to download. So.
Do you do all the training just on the ground and then upload the model, or do you update the models like during the lifetime?
Yeah, this is a good question. Right now we do just the first way. So we train them on the ground and then upload the software update if we want to change them. We don't have like online learning. This is like there are some experiments that this was done on board, but it's just experiments. I don't trust it a lot, because if you have like device that has power consumption 10 watts and you want to retrain the model on it, it will take like weeks. Yeah, so I think it's not possible right now. Maybe on the bigger satellites, or I don't know, where there will be like better hardware accelerations. I don't know where are the like constraints where we can go with this. So right now we are not doing it. It's like something that we don't see added value in. Good. Someone else? If not, so thank you for the. And now is the break, or you want to say something? Congratulate me, giving a gift?
Oh. Yeah, congratulations. Regarding the competition?
Yeah, so first of all, just a couple of remarks toward the end of our SpaceBeer. So, as you may know, this was the last SpaceBeer of this first round. Actually, we are really pleased to welcome you here, and we are glad that we could share some our knowledge with you. And I can see in audience some familiar faces. So I hope you learn something over the courses. And last thing, we need to select the winner of today's competition. So from the table, the name is.
Who is N.I.? N.I.
It's a bartender. Beeping his own house.
Okay, so then I would like Žluta Čepka, Dušan, come here. You're the second one.
Okay.
Enjoy this t-shirt.
Thank you.
Don't destroy it.
Should I take it?
Okay, so that's it for SpaceBeer. If you have anything that you would like to learn about more, or you would like to see SpaceBeer again, please send us a message and give us whatever topics you would like to learn more about. And hopefully us or the team coming after us in YSpace will organize something similar, or hopefully something even better, and we look forward to attending it. So thank you all for coming, and it was nice to see all of you. Thank you.